All right. Thank you, everybody, for coming to the Utah Go user group. Oh, we call it Utah Go Meetup. I don't know why that title slides that way. For November, do some quick stuff here and then turn it over to Brandon because that's why we're all here. If you have not heard of the spiel before, these microphones are really good. You might be whispering and thinking you're being quiet. You may actually be being quiet, but you'll still get picked up. They are fantastic, so just be aware of that. Yeah, so that's definitely on the recording. This is the part where I encourage everybody to go to our Forge channel and chat with us there. We just got the Slack update, so I'm there a little bit less, but hopefully they figure that out. If you want to speak here, please do submit to our paper call. Has been no talks rejected for I think the last year or so now. So if you have something you want to talk about, even if it's not fully formed, submit to us. We will work with you to figure out if it needs to fit in with another talk or series of talks, or if you just want to work on it. It is essentially open mic if you want to talk about Go. It's not like we won't ask any questions, but we will get you in if at all possible. And that's it. The rest of the time, I'm going to turn over to Brandon Atkinson, who works with me on the developer experience team here at Weave. It was just a short couple weeks ago. He was here talking about showing, honestly, just to brag, like some amazing pixel art that he built for the game that he built in Go for the GBA. Like the actual cartridge that somebody gave away. I'm still waiting on the order form so I can buy my own like version of Flappy Boot hard cartridge.
And spin up an Etsy.
Yeah. So I'm actually really excited about this. I've never seen a talk from Brandon that is not really impressive. He's got a really great skill for speaking. So we're happy to have him come up and talk to us today.
So, all right, we move over to my talk. And like Carson said, I was here a couple weeks ago. Speaking again. I enjoy speaking, but definitely feel free to come in and participate because I get bored of my own voice. I'm sure all of you are excellent speakers as well. And the other thing is like speaking is a skill that you develop by doing it. So this is a safe place to try stuff out, test stuff out. If you're worried about being recorded, we don't have to record your talk necessarily. Like, feel free to jump in, try speaking. It's a good skill to have, great way to network. All right, garbage collection goodies. So we are going to talk today about garbage collection generally, and also get into some of the specifics of garbage collection in Go. Garbage collection is famous as a language for including a garbage collector. And we work a lot with Go here at Weave and dig into some of the nuances. Like Carson said, I work with him on the platform team. So we build out the platform for all of our Go developers here, and we have to kind of get into the internals sometimes. And so knowing some of this garbage collection stuff can be useful. But we're going to start off today with a little YouTube, as every good talk does.
If you wish to make an apple pie from scratch, you must first invent the universe. Thank you very much.
All right, so super quotable. Love this clip. Carl Sagan was a great science communicator, very popular in the 80s, has a lot of really good quotable moments. This is one I really love. Points out the fact that there's always something deeper. A lot of the times we think we've gotten to the bottom of things, but there's so many layers that we build upon. And so as we discuss and think about garbage collection today, I want to kind of go back a little further than most talks might normally do. And let's start at the beginning. And obviously this isn't like the Big Bang. We're not going to go all the way back to the beginning, but we are going to go back to a time before computers really existed. Early 1920s, before the field of computer science was what we know it as today, there was mathematics. And there were mathematicians who were thinking very deeply about problems around computation and computability of numbers. And there was this guy, David Hilbert, who had some very optimistic and I think beautiful in some sense idea about mathematics and computation in the world. He has this very famous quote, I think it's engraved on his tombstone, is like, we can know, we must know. And this quote is indicative of his view of computation. So he believed, okay, that's gonna let him in? Yep. Great. So he believed that mathematics was computable. And to boil that down and simplify, essentially it means any problem that you could pose in the realm of computation, any question you can ask, can be answered. There is some algorithmic, some mechanical, some possible solution that you could arrive at in finite time to answer that question. And really the only thing holding us back was our own creativity, our own ability to conceive of better solutions. And this, like I said, it's kind of a beautiful view of the world and the universe that we live in. But if you know much about mathematics, and this question that he put was called the Einschüchterung problem. German has this really fun thing where they just shove words together forever until they get super long. I have no idea if I pronounced that correctly, but like this idea that he had, unfortunately, as much as it feels right, and as much as we would like to believe it's true, within his lifetime, this was proven to be false. There were many mathematicians that proved different aspects of it to be false, that there are logical systems where true facts exist that cannot be proven to be true, that there are things that are not computable. The one that we're going to talk about today, which is particularly of interest to computer science, is the Church-Turing thesis. Alonzo Church, the inventor of lambda calculus, and Alan Turing are the individuals who give this thesis its name. They're two separate individuals working on this idea of computability, the computability of numbers. In fact, I think that's what Turing's paper is called. And Alonzo Church goes about it using his lambda calculus, which he invented to show that there are, unfortunately, some questions which we can pose in mathematics which simply cannot be answered. And Turing arrives at the same conclusion. The mechanism by which he arrives at that conclusion, though, is very interesting. He proposes this imaginary machine, which we now know as the Turing machine, which has an infinite tape with ones and zeros on it. This is a reproduction. And it is infinite in length, and there is a mechanical head that can move across that tape, write a 1 or a 0, read a 1 or a 0, and it can be programmed. You can give it a list of instructions based on the data it's reading and writing for the things that it should do. And he, in this paper, proves this is the foundation of arbitrary computation. This is a computer, completely and fully, can do anything a modern computer can. This is the idea of Turing completeness. And then uses this machine to prove that you can take a program and feed it to a program and arrive at paradoxes if you try and compute the halting problem, which in this case is, will a program run forever or halt? For some simple cases, it's very easy to see how long a program will run, but for arbitrary cases, it's impossible. And thus we can show mathematics is not computable. Unfortunately, there are questions we can ask which are just impossible to answer. But what we get out of this is the basis of a revolution in computing. We have this idea now of memory, of reading and writing, of performing instructions. And in Turing's lifetime, we start to see larger and larger computers. On the left, I believe this is a replica of the machine that he built to break the Enigma machine code. You have IBMs that take up entire rooms. You have punch cards. We start to mature as a field and see more and more memory come at our disposal. We start with having to flip physical switches and have a very countable amount of memory and move very quickly to a realm where you are feeding in programs that you've written, and in some cases entering programs directly in a machine. One of my favorite anecdotal stories is during my, when I got my degree at BYU, I was reading a lot of papers and learning a lot about some of the early days of computing. And there's this story about a bunch of young engineers who are in this phase of computation where they're literally punching numbers in order to get the program to do what they want, right? They're punching the ones and zeros in essentially manually. And they have this great idea to program an assembler, right? This super high level construct we have of assembly instructions. Look, they're written in English. You can totally understand them, right? So they have this idea of writing assembly code and then running an assembler to get the output so they can run. And their mentor looks at this and he says, what a waste. You're wasting computer cycles writing an assembler. You should understand how the system works. Like, I don't know, this high level of abstraction was just so useless to him because he was like, just write it by hand. You don't need an assembler. A different perspective from a different time. So anyways, we have all this memory now. Programs are starting to get bigger and bigger. We're starting to get higher levels of abstraction. We go from an assembler to a compiler to interpreted languages, right? We're essentially moving up and up and up and up. And early on, we realize that we need a better way to manage this memory that we're getting more and more of. And so one of the data structures that becomes very useful is a stack. Stack is a very simple idea. It's essentially a list that is it LIFO or FIFO? First in, first out, FIFO. So you can push something onto the stack, you can pop something off of the stack, and it's a very useful data structure when we're trying to organize what memory is in use, right? Because one of the big problems is how do we know what memory has been allocated and is in use by the program and what memory is available that I can use at a future point in my program. Stack is great because allocation becomes essentially incrementing a single number, or in this case, decrementing. A lot of times stack is implemented with the high memory being at the bottom of the stack and low memory being at the top of the stack. It's done that way so the stack and the heap grow towards each other. That's an implementation detail. It depends on the system that you're on. But regardless, it's very easy to allocate more memory for your current subroutine because you just push a bunch of stuff onto the stack, increment a stack pointer, and you're done. All of the accounting that you need to do to figure out what memory is available has been finished for you. You can enter into the subroutine, do whatever you need on the allocated memory, and then pop off the stack when you're done with that memory. That memory is free for use again, right? Powerful, simple way for us to automate how we use memory and make it not so taxing to figure out exactly where every byte will live. But it turns out there are some limitations to a stack. Stacks are really good when we know exactly the size of memory that we're going to push on to the stack, when we have a very solid idea of, how much we're going to need to allocate. But as programs get more complicated, we realize, we might want to take arbitrary user input. We might have data structures which are of variable size. And we don't necessarily, memory's constrained. We don't necessarily always want to allocate the maximum size that input could be. So we want something more dynamic. Along comes another, we'll come back to this. Along comes another very useful data structure called the heap. So the heap is much less organized than the stack. Instead of incrementing a single pointer, there's a lot of accounting that you have to do. Blocks can be of variable size. Blocks can be out of order. And you have to do a little bit of work to mark specific sections of the heap as this is in use, this is free. You have to think about things like fragmentation. Is the heap in too small of chunks, or is it in large enough chunks that it can be used? How do I prevent the heap from being split up into a bunch of chunks, right? Because you can think of like, I'm allocating memory on the heap, and so I'm finding somewhere in the heap that is larger or equal to my size. Every time you find something that's larger, you split it up into smaller slices. There's a nature where we get smaller and smaller slices until we can't allocate anything because the heap's been sliced up into too small of sizes. How do we join things back together? There are a lot of questions surrounding how to correctly use heap. And yet it's a very useful construct, and so we continue to use it to this day, just like the stack. Really quick, the reason I have a thing about Stack Overflow here is there are some edge cases that you have to be concerned about when you're working with a stack, because if you use all of the memory available to you, you're going to end up with a Stack Overflow. And most of us have run into this with recursion. You'll notice that when you recurse through a function, if you accidentally forget like an end statement, you're going to run all the way to the end of your memory, allocate everything out. And we don't really tend to think much about this in procedural languages. It's more of a problem in functional languages where they don't have looping constructs. A lot of functional languages get rid of things like for and while loops and instead insist you use recursion for any type of looping code. And there are things that they have developed in that side of the computer science world to deal with the issues that come around stacked overflows. But they're not as problematic in the procedural programming world that we tend to live in. Okay, so back to a heap, context switching. One of the ideas that we had was, hey, there's a lot of overhead and decisions that have to be made when you're using a heap, how to allocate things and arrange things. We can actually offload some of those decisions to the program itself. And this is what we call an allocator. So it came along fairly early, right? C has an allocator. I'm not super familiar with languages like Fortran, but I'm sure it has a memory allocator as well. Like very early on, we have this idea that we can hand off the accounting of tracking what memory is and isn't in use to an allocator. And the way that an allocator works is it usually has two mirrored functions. In C, this is malloc and free. And malloc says, I need to find memory available in the heap. I'm going to walk through the heap. I'm going to find a section of memory that's large enough for the data that you want to allocate here. And then I'm going to give you a pointer back to that data and do some accounting as well. I'm going to mark that as used and make sure that nothing else writes to this data. And then you have the free call, which goes back in and finishes the accounting cycle. It says, hey, I'm done using this code or done using this section of memory. You can free this up for other objects to use. If you write or read from this memory, like it's not going to corrupt other parts of the program. Very useful, very nice. But just like with the stack, you can end up in situations where you blow your heap up. And how does this happen? Well, it can happen for a variety of reasons. You might simply run out of memory on your machine for what you're trying to do. But one that I think we're a lot more familiar with and is a lot more painful is a memory leak, right? We have these two mirrored calls, malloc and free, but if you forget to call free, the allocator has no way of knowing that that memory is free for use. And so you have ghost memory that stays around forever, fills up your heap, and then your program crashes. When your heap fills up, that's an OOM. You get killed, right? Oh, out of memory. So garbage collection then. We finally built up an intuition about all the pieces, how we're organizing memory. The next step we took was to say, oh, go ahead.
I just had a question. Maybe you know the answer to this, but do you know why it's called a leak? It seems like the opposite. Just go ahead.
What do you mean?
Like memory leak, and they call it a memory leak, but it's expanding.
Expanding, yeah. I think it's like,
It's less a balloon and it's more spilling out into the wild.
yeah. I don't know the exact historical reasons why they called it a leak. I think that they like conceptualized it as like use is like leaking out.
Yeah.
Like,
Yeah, I've always imagined it as memory leaking out away from your program.
yeah.
And access memory leaking away.
Yeah, well, because the way that you can think about it almost is like if your heap was a bucket, right? The usable memory that you have available to you is leaking away because the allocator has marked it as used, but your program can't get access to it. Like from the perspective of your program, the heap is actually shrinking, even though it's staying of consistent size. So I think that's kind of like the intuition behind it.
Okay.
But like, I don't know.
Sounds good.
Yeah, I don't know any historical reason necessarily. I don't have a cutesy, like, there was a bug inside the first machine that caused it to crash story. Even though that'd be really fun. I don't know.
You want the two theories?
Yeah, if you got an official answer.
Yeah, that'd be great.
In the ENIAC, very old thing, in the very old systems, memory was stored in circulating mercury. Something called a mercury delay line. Information was represented as a charge in a portion of mercury that circulated around tubes. The charge was read when that part of the mercury passed by detectors. This is also why the ENIAC could only use half of the memory. In this case, a memory leak is quite literal and fairly hazardous. The other theory comes from the mainframe days. Memory was shared between running jobs and was called a pool of memory after things like motor pools, secretarial pools, similar. When a job caused memory to become inaccessible, that memory leaked out of the pool. That I think is probably more likely, mostly because this is an operating systems term. When we talk about memory leaking, we're talking about virtual page memory, etc. Constrained jobs or applications or processes or whatever. So that's probably where it gained at least notoriety.
Certainly the mercury leak one is more fun.
Way more.
So in that sense, a memory pool is an anachronistic term
Yeah. Yeah,
I just held on to.
interesting. Yeah, because we have memory pools in what Go 118 introduced. the memory arena, I guess is what they call it, but. Okay, well, so the point of this talk, right? Garbage collection. We've arrived here at the garbage collector, and the goal, you'll see this quote all over the place when you start researching garbage collection. The whole goal of a garbage collector is to give a developer the illusion of having an infinite heap. There is infinite memory available to me. I call malloc forever. I never call free. I can leak memory into eternity. It doesn't matter because I have infinite memory. And just like the abstractions before, just like pushing a stack pointer or creating an allocator, we're trading off some flexibility. We're trading off some processing time to get a more comfortable environment to work within, right? And especially now as computers get faster and faster, and as the development around garbage collectors and even heap allocators has progressed, they've become significantly more usable. So that even a language like Go, which is considered a very fast systems level language in many ways, can totally get away with a garbage collection. So there are a couple of key terms that we're gonna want to talk about in the context of a garbage collector. There are lots and lots of different mechanisms for collecting garbage, but there are a few key terms that kind of pop up over and over again. So the first is tracing. And tracing is the way that the garbage collector figures out what memory can be recycled. So if you're trying to think about like, hey, I want to collect memory, or I want to recycle memory, how do I automatically find all of the memory that my program can never use again, right? What's all the memory that I'm definitely sure, no matter what runtime path I go down, I'm never going to touch again? And it seems like a very difficult problem, maybe even untractable. But the interesting thing is we already have some structure in place that makes it easier than you might imagine. We have things like lexical scope and a stack frame. And the key insight here is if you have as an invariant in your programming language that the only way to reach heap memory is through either a global scope or a stack frame, then you can simply trace the graph from those points into your heap and find everything that's reachable. Because if you can't reach it inside a stack frame and you can't reach it from a global variable, then it's just unreachable. And so this is the root idea of tracing is we're going to start inside the stack frame and find all the pointers, follow those into the heap, and then all the pointers inside that section of the heap, we're going to follow that into the heap, and we're going to bounce around into the heap until we've built an entire graph. We're going to do that same thing with all of the globally scoped variables, all the globally scoped objects, going to go into the heap and trace it all the way through. And usually in tracing, there's some sort of marking phase where we indicate, hey, like this is live. This is still reachable. In theory, my program could touch this memory in the future. Don't delete it. So the next thing is scheduling. And this is a very complicated aspect of garbage collection. And it's really the question of when should I collect my garbage? Because there are all sorts of trade-offs that you have to consider. The major one here is CPU time versus memory usage, right? The less often you run your garbage collector, the more garbage you're going to build up, the more memory you're going to use. The more often you run your garbage collector, the less garbage you're going to build up, but the more CPU you're going to use. It's kind of like the key trade-off. There's also considerations like latency, things surrounding your app. How long do you have to do a garbage collection cycle, things like that. But scheduling is a tricky thing when you're trying to figure out when should a garbage collector run. Escape analysis is not really garbage collection per se, but it is related to garbage collection. So escape analysis is a method for determining whether or not a variable needs to be allocated on the heap, and it can be statically determined at compile time. Compilers, the idea is a compiler is going to do escape analysis. And you can go both ways. You can use escape analysis inside a programming language like C to determine, hey, you've said that this needs to be allocated on the heap, but I can actually prove to you at compile time it never needs to live on the heap. So I'm going to optimize your code by putting this allocation on the stack instead. And in a language like Go, it can give you the illusion that everything exists on the stack because you just allocate memory the exact same way as you would allocate memory on the stack. And then the compiler will go through and say, oh, this needs to go on the heap. This needs to go on the heap. In fact, you can see right here, there are compiler flags. GC flags are Go compiler flags, not garbage collector flags. But you can use some flags to figure out, hey, what ends up on the heap and exactly why does that end up on the heap? Powerful tool if you want to try and optimize your heap allocations. So this is a way that we try and optimize away from using the garbage collector as much as possible, because again, garbage collector costs time. If you can statically determine you'll never need it, then why would you allocate on? Reference counting. Reference counting is a very interesting approach to garbage collection, and it gets used in languages that have real-time concerns. Like C has reference counting that you can use. Swift is very bought into the idea of reference counting. Reference counting is a method of automated garbage collection. Oh, Rust also is like bought into reference counting. You can do reference counted garbage collection in Rust. And the idea is like, instead of building that, like doing that tracing all at one time, right? We're gonna start a garbage collection cycle and like trace the whole graph. What if we like incrementally build that graph up? We're still gonna have to pay the computation cost of building the graph, but it's gonna come in more like smaller increments. We're gonna smooth out the performance of the garbage collector in a sense. And it's very simple. The idea is whenever you allocate something on the heap, you say there's one value pointing. And then anytime something in the program points to an object, you increment the reference count. You say there's another object pointing to me. There's another object pointing to me. And then anytime something goes out of scope or a reference is changed so it points to another object, you do the opposite. You dereference, right? You say there are less things pointing to me. And then whenever that value gets to 0, you know there's nothing pointing to me. I'm now free. And this is great. There's lots of really good reasons why you might want to use reference counting. Like I said, it's really good if you need to have a more consistent profile of your performance instead of having a garbage collector kick in and use a bunch of memory and CPU time all at once. There is like one fatal flaw though, one big issue that you have to tackle if you're going to do reference counted garbage collection in a language, and that's circular references. So if you imagine in our nice reference counted languages, we have a stack frame. We're going to push 2 new variables onto the heap. We're going to have blue and purple, and they have one reference each. Great. Then blue is going to be mutated so that it points to purple. Purple now has 2 references. Awesome. Then purple is going to be mutated so that it points to blue. Now they both have 2 references. And you can see everything is hunky-dory at this point because we have 2 arrows pointing to both blue and purple, and the reference count is 2 for both of those. Awesome, wonderful. The stack frame pops, right? We've exited the subroutine, we've exited the function, we're out of that stack frame, and we decrement the reference count for each of those objects. We have a problem now because it's not 0, right? There's 1 reference to each of those objects, but this code is completely unreachable by the program because if we can only reach it through the stack and globals, like there's no reference from the stacks or the globals. It's the heap is referencing itself. So usually to deal with something like this, even a reference counted language is going to occasionally kick on a more traditional mark and sweep style garbage collector. They're going to do some regular tracing algorithm to find all the circular references, or they're going to expect that you as the programmer are very careful with your code. And we know how that usually ends up. I'm sure there are ways you can design your language to get around this. I'm actually not really aware of how languages like Swift deal with this. They might have more clever mechanisms to prevent circular references like this, but like this is the Achilles heel of this type of garbage collection.
That's why Rust is so kind of regimented about borrowing and that kind of stuff is so that because it makes you make a lot of copies of a lot of things that you would otherwise just point to.
Mm-hmm.
I don't know if it's to work around this. Is Rust one of the ones that?
So Rust does provide you with the ability to use reference counted memory if you want to get around that copying things. My understanding is like you should try and avoid it whenever possible, right?
Does it use garbage collection?
Rust will use reference counted garbage collection if you explicitly ask it to reference count certain values on these.
Yeah, it's not part of the runtime.
Yeah, it's like a library that you would use.
You can add garbage collection to anything, but you don't get it for free from the runtime.
Mm-hmm. Yeah, exactly. Thank you. Okay, So mark and sweep is the first algorithm, very simple. And it's actually the one that goes garbage collector is based off of. So the way that this garbage collection mechanism works is it traces from the roots. So it's going to go from the stack and the globals. It's going to mark everything in the heap. That's where the mark and sweep name comes in. So it's going to go through a mark phase where it marks everything as the heap that is live and says, hey, this is still possibly could be used by my program. Don't touch this. And then you're going to have at some later point in time, it doesn't have to happen directly afterwards. There's going to be a sweep phase that's going to go through and say everything that's not marked as live, walk through and mark it all as free because it's free game, right? I can allocate here at any point that I want. And so it's like this dance between the garbage collector and the allocator where the garbage collector is trying to free up memory for the allocator to use. So this is what it looks like after a full mark and sweep. All the live objects are in the same places. We haven't moved pointers. That's not necessarily an essential part of mark and sweep, but demonstrated here, we're not going to move our pointers around, and all of our memory that wasn't marked as live is now free for use. There's also stop and copy. This is another potential algorithm in theory that's much faster than mark and sweep. I think it's been proposed as a way to get garbage collection in systems that have very low, very tight latency requirements. And so instead of going through the mark phase and then having a sweep phase that follows it up, you go through the mark phase and then you copy all of your objects into a new section of the heap. So this requires you split your heap in half. One half is the live heap. The other half is like the inactive heap. And you go through the mark phase, you copy things from the live heap into the inactive heap, and then you just switch the heaps, right? So you say the live heap is now the inactive heap. Everything in the inactive heap has been garbage that's now instantly collected. I don't have to sweep anything. And everything that was in the inactive heap, like I've allocated a bunch of stuff, that's all the live memory. So a couple things to note. We are, in fact, moving pointers. So your garbage collector has to be able to move pointers around. That may not be appropriate for the language that you're building. And you only get half of your heap. You don't get the full amount of your heap available to you in order to have that really, really fast sweep phase. There are some ways to get around this where you can have more of your heap than half available to you, but this is like the simplest implementation. Generational garbage collection is kind of a modifier on some of these garbage collection ideas. And it comes from the observation that most objects that get created are created, used very briefly, and then never needed again. Most objects die young. So again, you split your heap up into multiple segments. You have what's considered the old heap, and then you have the new heap. You can actually split it up into any number of segments if you want multiple generations getting older and older as you go back. But this is, again, simple implementation. All objects get allocated on the new heap. Anything new shows up in the new heap. And then at some point, like if we're going to imagine the scheduler just says, hey, anytime I fail to do an allocation, then I'm going to do garbage collection, right? You go through, you garbage collect just the new heap, and then all of the live objects, again, get moved and copied into the old heap. And the idea here is like most of your garbage is going to live in this new heap area. If your object has lived for a long time, the chances are good that it's going to continue to live for a longer time. So you do have to eventually pay the cost of doing a full garbage collection cycle on the entire heap. But a lot of your garbage collection is only happening on a portion of your heap every single time garbage collection happens because you're just mostly looking at new objects. I think a lot of languages use generational garbage collection as an optimization. I know Java does. I think Python does. It's a very popular optimization. Again, if you can move pointers. That's a big sticking point with a lot of garbage collection techniques you'll see is like your pointers are going to move. Your objects are going to move in memory. So languages that hide pointers have a much easier time of doing it. Mark and compact garbage collection, again, very similar to the ideas in the stop and copy or in generational garbage collection. We're going to go through, we're going to trace all of our live objects, and then we're going to copy all of our objects to the beginning of the heap and clear everything else out. Nice thing about this is your allocator doesn't have to worry so much about fragmentation because every time you run a garbage collection cycle, you're going to defrag all of your heap. You're going to coalesce a whole chunk of memory at the bottom of your heap for use, and it improves cache coherence because all of your objects are much closer together in the heap. So again, very common optimization inside garbage collection. Let's talk about Go, right? That's what we're all here for. That's what we all know and love. Go has a very famous implementation of the garbage collector and does a very good job of providing a lot of really good garbage collection features without moving pointers. Go doesn't move your pointers when you do garbage collection. So first, we are going to talk about TC malloc for a little bit. TC malloc is thread cache malloc, and it is a C library that became the basis for the heap allocator that Go uses. So this is the part of the program that's going to be allocating memory that the garbage collector is then going to later have to come by and clean up. Notice it's a little bit more complicated than the simple heap allocators we talked about earlier. It does a lot of stuff to improve performance, especially in coroutine heavy environments. If you're spinning up a lot of threads, you're going to be able to allocate memory, especially small memory, very, very quickly, because each thread is going to have, there's a per thread cache where you can go in and allocate memory into very quickly, very easily without blocking the whole heap for the whole program. There's all sorts of, there's a front end, middle end, back end that are all designed to prevent locking access to the heap memory as much as possible. And then there are all sorts of techniques that they use to try and prevent fragmentation. So you may have heard that the allocator in Go has a bunch of different size classes. I think it's like 67 different size classes of memory that it will allocate. So if you need a byte, it will go to a specific section in the heap that is dedicated only for allocating bytes. Or if you need something that's like 32 bits, it'll go to the section of the heap that's like, all of these are 32-bit numbers, right? And so that helps it to be very, very quick to allocate and to deallocate and prevent fragmentation in the heap. TC malloc also is notable because it will not free memory back to the OS. Once the OS gives it memory, it holds on to it forever. Interestingly, Go remedies this, and Go actually will release memory back to the operating system after 5 minutes of disuse. So if you have memory in your program for 5 minutes, the Go developer added this feature where it will go out and it won't get rid of the memory, but it will tell the operating system, you're free to collect this memory whenever you want it, right? So you will get that, that heap size shrinkage if you're not using memory. Okay, so now that we have some ideas about, and I would love to go in tons of depth about the garbage or the heap allocation. There are some really cool talks about how the heap allocation works, but I just don't know that we would have time to do it. And so instead, we're going to skip into garbage collection. And you might be surprised to know that the garbage collector is fairly underspecified in the Go specification. Go basically says, hey, the language needs to manage memory, but other than that, leaves it totally up to the implementers of the compiler to decide what that garbage collector looks like. And it says this omission is intentional and enables the use of radically different memory management techniques, right? So this talk may be totally obsolete in 10 years because the Go team might have decided we're going to use a totally different garbage collection mechanism, which I think is kind of cool and forward thinking. And also it allows things like TinyGo. Last time I was here, I talked about building some stuff using TinyGo, and they use a completely different garbage collection scheme than the main garbage collector because they need a smaller garbage collector with different runtime properties than something like a fully fledged language would. There's also, I didn't even realize this, but there's like 2 or 3 other compilers for Go. There's Go LLVM, there's GCC Go, each of which uses their own version of garbage collection, and all of which have kind of their own niches kind of built on the Go language spec. So multiple compilers for Go, garbage collection is different in each of them. We're focusing today on garbage collection in the main Go compiler. So again, it uses these very common things that pop up in a lot of garbage collection technique. It's heavily reliant on escape analysis. The compiler is what determines whether or not something ends up on the heap. You as the developer never make that choice. Tracing is a big thing. It's going to trace from the roots into all of the live memory to figure out what memory can and cannot be reached. There's a lot of cool things that they do to speed up tracing and make it work in a way that is concurrent with other processes that are running. And then GC scheduling. They are very aware of the trade-off between CPU usage and memory usage. And we were talking a little bit earlier before we got in here about how Go historically has been pretty tight-lipped with they are pretty miserly about the configuration ability they give you for garbage collection scheduling, because they have some very strong ideas about how that should work. There are a couple of knobs that you can turn to change how garbage collection scheduling works in your programs, but generally the defaults tend to be fine, and the Go team feels that way too. So memory versus CPU, this is the big trade-off that we have to think about. We talked about this earlier. The more often your garbage collector runs, the more memory you're going to have available to you, or rather, the less memory you're going to use in whatever environment you're in. But the more CPU time you're going to spend doing garbage collection. And that's an interesting trade-off depending on where you are running and what your constraints are. So let's go and look at, and I might have to share this tab instead. Let's go look at this document, a guide to the Go garbage collector. This is really great. I recommend that if you're interested in this talk, just go read this. It's actually not that long to read through the whole thing, but it has these really excellent visualizations that you can use to get kind of a more intuitive sense for how the GC scheduler works. So here's this graph that has in dark blue live heap. So live heap is all of the memory that your program could access at some point in the future, so we can't collect it. We can't classify it as garbage yet. And new heap is all of the new things that are getting allocated on the stack. Here you can think of it as like, this is all the garbage that is getting created, right? And you'll see at the bottom, garbage collector CPU usage, 6.5%, peak memory usage, 40 megabytes, and peak live memory usage is 20 megabytes. And then you have GoGC. So GoGC is an environment variable that is respected by the Go runtime, which you can use to change how aggressive the garbage collector will be in attempting to collect garbage on the heap. And you can see the actual formula that they use to determine when the garbage collector will run is right here. So they look at live heap, GC roots is like that tracing algorithm. They take this Go GC value over 100, and like that's the target heap. And the goal is that the garbage collector will run before the target heap gets hit. So we can see that we're using about twice as much memory as we technically need to. In our heap, we're using 40 megabytes, but the live memory is only ever 20 megabytes. So let's say that we wanted to be more efficient with the memory we were using. Well, we could change GC and run garbage collection much more frequently. Here you can see that now our max memory usage is under 25 megabytes. But you can also see the impact on the CPU. Now we're using 25% of our CPU time to collect garbage. And you can see every single one of those spikes is the garbage collector kicking on, tracing through all the routes, doing all the work of garbage collection to keep our heap size low. Additionally, you might say, well, I care a lot more about how burdened my CPU is than about how much memory I'm using. So you can kick GC up in the other direction and say, like, yeah, you're free to grow all the way to like 150 megabytes. I don't care. And it's going to be really expensive to collect that garbage, but it's only going to happen a handful of times. So you can see 1.6% of my time is spent doing garbage collection. That's very low. So if you are willing to sacrifice more memory than processor time, you might consider bumping that up. And then as you get to the very limits of this, GC off basically says just allocate and never deallocate. And so you can see like, this is why we need a garbage collector, because otherwise our memory grows so crazily and you can't even see the live heap anymore. All of our program is garbage. So really fun to see this. This kind of demonstrates what it's like when you have variable loads. Like, look how much your garbage collector has to start kicking in if you start allocating a ton of memory, right? Like we're allocating at a normal rate and then something happens and we allocate like nuts. And like we're eating up our CPU like crazy doing garbage collection. So this can be a real cause for concern if your service starts suddenly allocating a ton of memory all at once. Another interesting scenario that you're probably going to run into, and a lot of these are like contrived and simple. You can read about it in the article, the way that it works, just mostly to help you get an intuition for how things are working. But like this example, they demonstrate what happens if you have a sudden spike in heap usage, right? Maybe you get a rush of requests to your service, or suddenly you need to do a lot of processing off a queue and you need more live heap. How does that change the profile of your garbage collection? And again, you can see like, just like normal, if you garbage collect more often, that's going to be a smoother ride up to the peak and a smoother ride back down. And if you let garbage collection happen less often, you're going to see less of that peak, but you're going to have higher kind of live heap. The interesting thing is, in order to deal with this specific scenario, the Go developers added a new toggle basically that you can use to configure your garbage collector called the memory limit. So you can imagine saying like, hey, I really don't want my CPU to run a ton, but I also am in a somewhat constrained environment and there's a hard limit. Like I can't go over 50 megabytes. And that's totally fine, like 90% of the time. But every once in a while I'm getting OOM killed because my garbage collector isn't jumping in time. So you can actually come in here and say, I'm going to set my memory limit to like 50 megabytes. You can see my garbage collector is going to jump in a little bit more early than it normally would have because it knows like this is my peak, this is my max. So you do pay a little bit more CPU cost, but only when your heap spikes. So it can be a nice toggle for dealing with programs where you're going to have kind of spikes in your heap usage. One thing to be really careful about is as you configure these, be validating that they're actually like working correctly, right? You want to make sure that you're profiling your garbage collector. And if you're setting these things, you should have a pretty good idea of the performance of the garbage collector. And B, you want to avoid situations where you're actually going to like kill your program by thrashing the garbage collector. So go ahead.
So what do I see in my program's behavior before I start playing with these numbers?
That's a good question. Well, okay, so that actually leads me really nicely into the next slide. You might just see that it's not performing fast enough. Like you might just have a general like this is not pulling out enough messages off of NSQ. This is not handling requests fast enough. You might notice that like your memory usage is really, really high, right? Maybe your program it has like a lot of really spiky memory. And so you're like, yeah, for some reason we're like spiking up and using a ton of memory for a little bit and it takes forever for it to go back down. I don't really know in particular, like you might have a sense that you might look at a program and be like, it seems like it's using an awful lot more memory than it should, right? It seems to me a little bit more like you just have to be in it and kind of know where you're at a little bit more than like, I don't have really good general guidelines in part because I've never done this, right? Like we've never run into a situation where we've run into a very small number of situations where some things were obviously wrong. And then we had to dig into things, but like that was situations where program was like running fine and then suddenly out of nowhere it would get OOM killed, right? Very quickly. We're like, what's going on? What's happening? And a lot of times the solution there is actually not to mess with the garbage collector. It's to rewrite your program to allocate on the heap less often, which I'll talk about in a little bit. But like, yeah, I don't know that I have good general, I don't know. Do people have ideas for like, what should I look for before I start messing with the garbage collector?
I guess maybe if you want to trigger scaling by CPU usage, I guess.
Yeah, maybe if you want to, yeah.
So I think the memory limit was added explicitly because containers will kill you. Like you've specified you're going to use this much memory. If the garbage collector doesn't know that and is instead said, oh, well, I'm going to try to keep in this, but I'm going to double the allocation by default just so that it's easier on the CPU, that's where you run into those kills. And so I don't know if they do it by default yet, but if you're in a container that has specified I will only ever use this much memory and you're in a tight environment, it is something that you could then memory side. More often than not, you're probably, so there is metrics on this. You can actually see how much time you're wasting on your GC. And there's probably some threshold. If you're running a bunch of Go apps, you'll see what it normalizes it. And then you might see outliers and addressing the outliers, but don't address them necessarily directly by just tuning the GC. Stop making the garbage. Like excessive garbage collection is something he'll probably talk about.
Yep.
That's actually a cause of a problem, not something that you should be able to actually tune away.
Yeah. Matt, did you have ideas?
Oh, I was just saying that one of the things they called out here is that if you actually tune the memory limit, you can turn the GC off and it will basically just run the GC when it hits the memory gap.
Yeah. So you can basically only run your memory or your garbage collection when you've hit your memory limit, right?
Probably incur more of a pause maybe
Yeah.
each time, but
if you throw out less garbage, it'll never run.
Yeah. If you never make garbage, if everything is on the stack, then you're fine. Garbage collection is unnecessary.
Yeah, I would place tuning garbage collection with one of those, like, in that big list of things that like you can probably worry about, but really almost never need to. Like, don't optimize till you hit the point where you're looking at a thing saying, how do I X% more performance out of this? Like, if you get it too quickly into the space of like, well, this is slightly less performant than this, like, that's probably not the most important thing you spend your time on most of the time you're writing. Like, how often are you writing code that's called 10,000 times a second? Like, you're really usually just writing stuff that's fine to be good.
I mean, I'll tell you why.
Readable before you make it more performant.
Yeah.
That'll be paid dividend.
I'll tell you why I got interested in the garbage collector, because I wrote a game for the GBA, and when the garbage collector kicked in, I dropped 3 frames in my game. So I was like, well, how do I optimize the GC, right? Because I had already eliminated basically actually the way I solved it is I eliminated all my heap allocations, right? But yeah, it's like, if you're not running on a GBA CPU, like, there are some very specific cases where you need to tune the GC, but most of the time you want to focus more on like what's causing the garbage.
I'll also point out that the Go garbage collector tuning is very different than like most other languages that you might find wisdom on the internet for. Like Java is the elephant in the room for that, but even Java, like the garbage collector performance has really increased quite a bit over the last 25 years. And that's great, but it behaves very differently and you encounter very different scenarios for tuning it with its weird knobs than the Go garbage collector. So don't just apply universal garbage collector wisdom to your Go environment, build the profiling, find out what your use case is, etc. Chances are you won't need to tune this very much, if at all. And if you do, you will be doing a lot of thinking and diagramming and worrying about math and stuff that you probably don't want to even try to do early.
One of the things they call out in some of the garbage collection literature for Go is like they were running into a problem when you had more than like 100,000 Go routines or something. And like then garbage collection became an issue. So it's like, yeah, if you're on the edge, if you're doing really weird stuff, maybe not really weird, but if you're doing really intense, high volume stuff, then that's when you would want to dip into it. But like most of the time you want to, and again, like that's one thing that I really wanted to talk about. Like before you blame the garbage collector, like you should always try and validate first, right? There's pprof, you can do CPU profiling, GC tracing, you can get execution traces, right? Like if you think that the garbage collector might be a problem, the very first thing that you should do is pull out pprof, right? And really do some hard validation. One, because then it will actually show you how to tune the garbage collector, but 2, then it will show you like, yeah, you've definitely made an improvement, because it can be really tempting to just be like, oh yeah, if I just, add this memory limit, it will definitely make things better. And it made things worse, but you never checked, right? So make sure you get some hard data. And again, like the first thing you should always try and do is make less garbage, right? You can go through, use your go build flags. It will tell you, give you some really actually like very parsable, readable and reasons as to why, like, hey, this thing escapes to the heap. I have to allocate it on the heap. And so you can usually follow through that and be like, oh, can I reuse some of these objects? Can I allocate less things on the heap? And it's a lot of times not even that ugly in your code to just refactor a little bit and prevent things from ending up on the heap. There are other tricks that you can use, like the tracing algorithm will stop tracing through a struct at the last pointer it finds. So you can stick all of your pointers at the top of the struct to slightly optimize garbage collection. And memory that doesn't contain any pointers is siloed into a completely different area that the garbage collector doesn't even know about. So if you can copy a value, it optimize the performance of the garbage collector because it never has to touch that memory. But yeah, kind of as a last ditch effort, you might consider setting the GC% or setting the memory limit. And then you also have to be really careful because the Go runtime respects these flags, which means if you release a CLI tool and you're like, I've tuned it so it's like perfect and garbage collection is really great, somebody can go set Go GC on their own system and totally ruin any optimization you made because that's now what the Go runtime is going to use for its GC%. So like, it shouldn't necessarily be, should be one of the last levers that you turn, which I think is why Go has been really careful about giving a lot of tunability to the garbage collector. Cool.
You also pools, right? Like sync pool, the being able to allocate and say, okay, the pool is for like ice buffers. And all the ones that it just, you don't have to really set it up necessarily. You just say all the ones that are being used, it expands the pool. And then when it needs to get new ones, it looks for empty ones.
Sync pool is great. Memory arenas are another option to try and avoid the overhead of the garbage collector. So there are lots of tools outside of tweaking performance. But it's good to know how that stuff works even, if you are in a situation where you're running Docker containers, right? Maybe you should set the garbage collector based off of memory limit.
Is there, so I'm thinking about this, if I were, I don't know, built tools that deployed services. Would there be a reason not to just set the mem limit to the memory limit of the container? Like, is there any extra? It's a good question. Like, why not just I know what the limit is, why not just set, I would want to keep the normal garbage collection on.
So this is why you might be a little concerned about setting the memory limit. It's called GC thrashing. So what can happen is if you set your GC limit very, very close to the live heap size, right? Like here, my GC limit is 30.5 megabytes and my peak memory uses is 30 megabytes. You can see the garbage collector is basically like clicking over and over again. So this heap spike can lock up your program and make it completely unresponsive. And so actually the way that in practice Go does this is they maximize the amount of time your program can spend garbage collecting at 50% of your CPU. They will let you get OOM killed instead of getting GC thrashed. But you might be thoughtful about just going ahead and setting the limit for everybody to make sure that like, I'm not going to accidentally lock up my program and then make it completely unresponsive, but it's still alive because that can be much worse than just, oh, I'm killing it. So that's really the only thing that I would say maybe would need to be careful about. And again, Go tries to prevent this by maximizing the amount of time you can spend collecting garbage. But yeah, there might be some like validation you would want to do, like maybe tracing how much memory is used in the heap and then being a little bit maybe generous with that heap or with that memory limit so that you have headroom in case heap grows unexpectedly.
Really, you just need to narrow down, can your app handle killing itself or GC thrashing
Or swap. So like memory is actually something that even when it's live, it doesn't necessarily ever get accessed. And so if you just have a bunch of SSDs and you want to say, well, we'll just swap out pages that aren't being used, then you never have to get them killed. And as long as you aren't actually using every single byte that you've allocated, you might be fine. So that if you're a VPS provider trying to over provision everything to squeeze as much juice as you can, you might do something like that and just say you're gonna get a shitty performance. Like you'll start swapping, and every time you read bytes that weren't actually in memory and had to come off a disk, your CPU waits forever for those. But there's a lot of things that might do weird things, like allocate a ton of memory and then never use it. And you could paper over that with just swapping it out to disk.
Also worth noting that none of this will save you from a memory leak for the same reason. Like just going up, but if things is all being used, that's
Yeah.
crash.
Unfortunately, the illusion can be broken. The illusion of infinite memory.
Uh-huh.
You know, I started off this talk with like, we're starting from the beginning of the universe and we're going to build everything up. Maybe something comes after GC that gets us closer to the ideal of.
We just have infinite memory.
Yeah,
That was the thing.
we access pocket dimensions and there's just infinite SSDs. I
We
don't-
just never actually need to collect because you just have it forever.
Yeah. One of the other things that is important to talk about, we talked a little bit about like why you might want to configure the garbage collector, some thoughts that you might have about like keep in mind if all of that memory is used and like if virtual swap is happening and everything. I also just wanted to call out this idea that like latency is not CPU usage. And so sometimes you can get trapped in this idea that like, oh, I'm using like 10% of my CPU, but you know, if your latency is going down, right, you're able to serve requests more regularly, it's probably fine. And one of the reasons why Go, as a language that does a lot of HTTP servers with low latency, is able to use a garbage collector, because again, what matters more is the latency a lot of the times than the CPU usage. And in general, the general rule is reducing garbage collection frequency may also lead to latency improvements. So if you're kicking the garbage collector on less frequently, overall your latency is going to be better, even though you'll probably pay a little bit more of a CPU price when garbage collection does actually happen. Again, like that is up to your domain and depends on what you're doing. But latency does not equal CPU usage, so keep in mind that those are two separate metrics. Okay, last thing we're going to talk about, and we're going to speed through this because I'm kind of at the end of my time, but the Go garbage collector uses a really interesting concurrent method to do its mark phase. So we talked earlier about mark and sweep. Mark is where you trace from the roots through the heap to identify everything that's live. Sweep is where you wipe away everything that has no possibility of ever being accessed again. So you have your Go program running, it's allocating to the heap, and then a garbage collection gets scheduled. So what happens? Well, the first thing is it marks the whole heap as white. And we'll talk about what white means in a little bit. And it puts in a write barrier. So this is a stop the world operation. Go's garbage collection is as a whole pretty concurrent, but like this phase and then one other phase is like stop the whole world. Everything has to be stopped. All of your Go routines have to be paused because I need to put a write barrier in place. As soon as that write barrier goes in and all the memory is marked as white, we start executing concurrent code again. Garbage collector is running along with your user space code. The white set is, the goal of this algorithm is that eventually the white set will contain all the garbage. And then there's a black set that will contain all of the live objects. And then there's a gray set that we will use to mark objects that have work still to be done on them. So we have a bunch of white objects. We're not done with the algorithm yet. We trace from the stack into the heap and mark everything that we can reach as gray. We add all of that to the gray set. Additionally, what that write barrier does is anytime we write new memory, I was a little unclear about this. I'm not sure if it marks it as gray or black. We're just going to assume it marks it as gray. And gray means, hey, this is reachable, but there's still work to be done to determine what can be reached from this point. So we're tracing all of our gray objects, and then in like a very Go routine style fashion, right, we just pick up all of the gray objects and trace the gray objects to the white objects. Once you finish tracing an object to all of its children, you mark it as black. And then again, all of the objects that you trace to are gray because they still have work. You need to see if they're connected to anything. And you do this algorithm over and over and over again. You see you have like these these kind of 3 separate spots in the heap. Your black set is everything we know can be reached. The white set is like, this may or may not be garbage. And the gray set is like, we still need to work. Like, this is the stuff that still needs to be worked on. And black objects will never point to white objects. Like, the gray is in there to bridge the gap. And as you continue to work, you're going to mark more and more of your objects as black until the whole graph has been covered and there's no more gray objects. And once there are no more gray objects, we have black and white, we know tracing is done. So white, everything in the white set is garbage. Everything in the black set is live memory. And the garbage collector shuts off and tells the scheduler, schedule some sweep to happen some point in the future. Like, I think older versions of Go, this could last like minutes before your garbage actually got cleaned up. It would like find garbage, mark it as garbage, and then just say, hey, schedule the sweep phase whenever you want. But that's it. That's the full, I mean, that's the very high level version of the tricolor algorithm that Go uses. And it can do this concurrently. It uses a bunch of Go user threads, right? Like, one of the things that happens during the garbage collection cycle is it will actually go steal some of your Go routines to help with garbage collection. A, so it gets more CPU time to work on garbage collection, but B, it also stops you from creating so much garbage so that it can do the garbage collection in a reasonable amount of time.
I thought they even stole more. The more garbage you create, the more of your time that it can end up stealing.
Yeah. So not all of your Go routines are purely yours. Sometimes Go is going to steal them for garbage collection work, but it allows it to run concurrently and very quickly. And yeah, especially in cases where you are going to have a lot of threads running, a lot of Go routines running, it can be a very efficient way to do garbage collection because your code can still run concurrently. You can still read and write from the heap. One thing I forgot to put in here is after this phase, there's the write barrier is taken out. That's also a stop the world operation. So all of your Go routines get stopped when garbage collection kicks in. And then when it's finished, it also stops everything so it can take that write barrier out.
What you do want, by the way, like if anybody's thinking, oh, why can't we make that thread safe? Like, no.
There are good reasons, yeah, why that write barrier is not a concurrent operation.
Several orders of magnitude different performance. That's the key.
Yeah. Cool. Well, thanks everybody. Appreciate you coming. Any questions?
You need a slide at the end, so
I know, I forgot to add my final slide. I apologize.
So where's the best, don't do these stupid things for garbage collection list?
Sorry, what?
So what are the non-obvious things to avoid to be nice to your garbage collector?
the common mistakes of that make garbage that you wouldn't know make garbage.
One pattern that I see pop up a lot is returning pointers everywhere. And that can potentially get you into trouble because when you're returning pointers everywhere, you're creating a lot of stuff on the heap that can cause issues. A lot of like, if you're creating a bunch of slices or maps, things like that. I was talking earlier about like in-game development, you're running at 60 frames a second. So it's very easy to create a lot of garbage very quickly. If you're like, oh, just create a string every frame, like we're just going to recreate the string every frame, right? That's going to end up on the heap and you're going to fill your heap up very quickly because you're doing that a bunch. The big thing I think is like, I wouldn't recommend that you write a whole lot of stuff in C because it's hard. But I would recommend you learn C, specifically because it's kind of hard to get a sense for where you might be doing dangerous things when you've never actually had to do the work of figuring out what does and doesn't go onto the heap, right? Go does a wonderful job of giving you the illusion that everything is stack allocated. But yeah, like, I don't know, building up that sense, and I'm sure you can tell, like, I don't really have that strong of a sense because I haven't done a whole lot of programming in C, but like, if you can find projects to work on or areas where you can like go and work without a garbage collector, it kind of helps to build this intuition of like, oh, hey, this probably is going to end up on the heap. This is going to create garbage because I'm doing this function a lot in a hot path. I should maybe avoid that.
I'd definitely say, so the garbage collector is there because you shouldn't have to care. Majority of the time, if you're not in a hot loop or not allocating gigabyte strings, you really shouldn't have to care. When you are in a tight loop or you're processing web transactions and you want to optimize the throughput rate, how many transactions you can support per server. it's actually better to just focus on that. Don't care about anything else and benchmark it. So Go has some of the best benchmarking tools that you can say, here's a transaction. I'm going to simulate one transaction. Oh, this is allocating this much memory. Can I reduce that? And so you can do it with unit testing and just focus on the hyper pop. Get that as optimized as you can and don't care about anything else. Because on the program startup, even if you leaked 50 megs and then 5 minutes later it garbage collected it away, who cares? But if you did that through every cycle of a HTTP request, you're definitely going to run out of memory. So find the hot loops, benchmark those. It will explicitly tell you when and how you're allocating. And if you can reduce those or use the tracing tools to be like, oh, well, if I changed how this algorithm worked, I could do something. Sync pools are the easiest thing. Of like, oh, I need this resource is a meg. I need a bunch of them. Well, just create a bunch of them and then reuse them. And a sync pool will just let you keep reusing it instead of making them, throwing them away, making them, throwing them away.
So for benchmarks, you're specifically talking about writing benchmark tests.
Have a unit test that says, here's my HTTP
Benchmark
transactions.
tests, yeah.
And then you can run that in a benchmark really easily. And you can easily tell if you made a change that made that allocate more memory. That's something you should probably care about because it's going to make your overall performance slower because you'll have to garbage collect more. Okay? And so by treating it as this is the thing I care about, I will focus on this thing. It's a lot easier than like, how can I never leak memory or how can I never allocate memory? Well, go write C if that's what you really want to Rust. Like Rust will do the math proofs to prove that you aren't going to leak the memory or have to collect the garbage.
In some ways, I envision garbage collection, like optimizing garbage collection is a little bit like optimizing your heap allocator. Like, yeah, there are people who are thinking about like, what's the best way to allocate memory on the heap? But it's a very small number of programmers and probably for good reason. Like you're probably fine. Like, your allocator probably doesn't need tuning.
It's a good problem to ignore until you actually have that problem to pay a bunch of people to solve.
Yeah. 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 And it's just, the Go garbage collector does such a good job that for the majority of use cases, even if you're writing bad code, you're probably not going to run into issues. Like,
Yeah, write really bad code.
yeah, you gotta write bad code in like a critical area. Yeah.
Kind of global stuff or package level stuff.
But it seems like the rule was that if you're in a tight loop, you have to be careful about allocating memory that escapes the front stack frame or whatever.
Yeah. Well, and then like a really tight loop, right? Like if your tight loop is, this is gonna run 20 times really fast, but.
And Carson touched on it earlier, a lot earlier about the readability versus the optimization. Like it's, if I were to get something back from a programmer and I'm reviewing it and it's like not very readable, but it's got these benchmarks and everything. Like it's clear that a lot of time was put into, a lot of time and care was put into benchmarking and less into like, how is this going to not be a nightmare to do upkeep on?
Yeah.
And I would rather time be spent on the readability and then follow up with benchmarking if necessary.
This is called once an hour and you've got like 20 benchmarks on it. Can you tell me why?
Yeah, in general, I mean, there's lots of academic research that has gone into it. There's lots of engineering hours, so that we don't have to think about it and we can write bad code. And like really, the truth is a lot of times clean, like not clean code, but like really parsable, readable code, a lot of the times is not the most performant or even very performant at all. And as an engineering discipline, we've worked really hard to make that code viable, right?
Like, yeah, classically there's cases where like a go-to in a right place can massively improve performance. But if I see go-to in any code that I'm reading, I'm like, just incur the cost of like, put this in a function. So the logic is simpler. Yes, you have another function call you've just added that you didn't need if you did something fiddly stuff with scoping and variables. But like, yeah, it's just, I think it does speak to the fact that like, we almost never hit these things in Go. As Todd likes to say, Go is guardrails the language. And I appreciate it for that so much.
And it very much depends on your domain. If you're writing a game engine, if you're writing a physics simulator, this conversation is, I think, totally different.
So you're writing a game engine and you chose Go.
No.
He did.
Well, I wrote a game engine for the Game Boy Advance in Go, and I wouldn't, I mean, I made it,
I'm gonna make that decision again.
I wouldn't make that decision in any production environment. If I wanted to make money, I wouldn't do it in Go. But if I wanted to have fun, that's a totally different set of
rules are a lot more
requirements.
constrained too, because like how many times are you getting random allocations from end users in a game? Like maybe if there's a chat system, yeah, but like an actual Game Boy game,
Mhm.
you might be able to actually statically pre-allocate everything and never have to deal with garbage collection. Just knowing that like, oh, here's where I can load these sprites. I get 5 slots for that. I get that. It's a lot more deterministic. Whereas when you have to say, oh, someone's going to upload a file to me. Okay, I have to have a place to put that, and I might want to put that on memory, and so I can process it. And now you have this non-deterministic thing that comes into play.
So it's the garbage collector that would scare you away. And you can obey the rules, not have the garbage collector scare you.
My favorite example is so even .NET and the IIS web server, they just decided like, we'll just run web processes for 27 hours and then we'll stop receiving new requests and we'll shut them down. So if you can survive without it will cause a problem and within 27 hours you'll get restarted, like go do something else, like make your time more efficiently spent by improving your product.
I've worked at companies that solve problems with that exact thing, just a max lifespan to solve a memory leak. Like, look, we're really good at making new versions of this. We'll just restart it every hour. Like, it's actually easier than fixing the leak.
If you
The
are
best garbage collector is shutting down the computer.
Unless you're using 100 gigs and you need 200 gigs, that's not gonna cost you that much more. If you're using 2 terabytes and need 4 terabytes, then maybe you're getting to, but like the numbers are getting crazy big, and really until you are like, oh, well, we need to do this 1,000,000 times and we need it to complete in a minute. Okay, now you need to care. We need to do this 1,000 times, and if it's done in an hour, we're fine. Computers are crazy good now, and like you probably don't have to really care or think about it.
Although sometimes I do wonder how much of this ends up with like, everything is shipped in Electron. Chrome takes all of my RAM, but like, maybe a discussion for a different time.
Well, and then it just pages it out to this. If you're actually not live scanning that entire set of memory, now you can put it on a hard drive and you can get 5 terabytes for $100. Like it's.
Well, we're gonna.
Yeah, I put the thinking slide and I added it.
Great, Brandon, thank you.
Thanks for coming, guys.
Close up and have real chat.
Yeah, now you can, wait,